So, good afternoon, all. Today, this is our last session. Yesterday, also, I have posted one quiz. Still, quiz on moment of inertia, or you can say second moment of area is remaining. So, today, I will post it also. And quiz on forging is also remaining. So, after completion of this session, so we can uh, do that also. Okay, means there will be one more quiz regarding forging, right? So coming to our subject, yesterday we have seen how to design a forging component. Means we have first seen what is forging, try to understand forging process, means how it is done in industry. We have seen some videos also regarding forgings, and then we have in design considerations for the forging, right? So we have seen one example of flange and what are the design considerations for that flange, like parting line or suppose draft angle is there, machining allowance is there, different parameters we have seen and what is use of these parameters and while creating 3D model of how this can be useful that we have seen. Means today we are going to design one component. Yesterday I showed you some component like I will share that again. So these are the two images where one is machined component. So this one is machined component as we have discussed yesterday. This is ready to use component and there are different features. All the this, you can say machine design, machine model or drawing. Okay, and this one is a forging component, right? So using this as an input, forging industry designs these components and create 3D dies out of this. So we are doing this process using CATIA today. So generally this machine model or this type of model is supplied by the customer. Okay. And they give the IGS model of these components and we have to create forging model. Okay, but right now we don't have this model ready with us, so we'll create this model using CATIA. Means again, we can go through some features of CATIA also while creating machine model. We will convert it in IGS model, which is a neutral file format, and we will save this component as IGS file, and we will try to convert it into forging model. And again, we will create a die, okay, upper die and lower die for this component, right? So we will start with CATIA. So I will just open CATIA software right now. I have drawings of these parts, machine component. Meanwhile, let me share this drawing also. So you can see this drawing. This is a machined drawing, machine component, machining drawing, let's say. Okay, and this one is the forging drawing. Okay, so this one is the forging drawing. Forging drawing is ready with us, but we are going to generate forging model using this machining model. Okay, means we have this machining component or machining drawing of that finished product, and using this we can create the 3D model. Okay, you can just go through this drawing. You can see different GD and T feature control frames are also used there. Okay, see this. So we create 3D model of this component, machine model, okay, using CATIA. So we start creating this model first, and then I will explain you how to make the die out of this, right? So I will share the screen of CATIA first, and then we will start with this model. Okay. I'm considering that everyone is having knowledge of CATIA, I think. So, okay. So this one is user interface of CATIA assembly, means CATIA product environment or product workbench. CATIA by default starts in product workbench. So I will just close this environment and we will start a new part. So I will go to mechanical design and part design. Okay. So this component is a flange. So I will give a name here, flange machining. Okay. So here, this is a specification tree and you can see the part name here. Here also you can see the same part name. So when we save this file, it will be saved with this name by default. So we'll save it first. So we are going to create a machining model, right? So it's a circular component as you have seen this component, you have seen the image also, you have seen the drawing also. So we start with the SketchUp. You know how to create a SketchUp. So I'll go to Sketcher environment. Here I am using position sketch on this YZ plane. So okay, first I will create axis because this is a circular component. So we are going to use shaft command, right? To create circular components, revolve features are used. So this is a shaft command. This is the basic section of the component. Just without dimensions, I have created the sections. Now we'll apply all the dimensions or you can say constraints. Okay. So these are the dimensional constraints. From this axis to this, I will apply diameter here. Again, this diameter is given. This diameter is also given. We are going to create here basic shape, not a complete component. Okay. So then I will apply distance, this distance. Then this much height is also given to us. And height from base, total height is also given to us. Right? So these are the dimensions, and now we can see the geometry is constrained. We will just apply the, we will change the values as per the requirement. This diameter is 87.38, so this we will change 87.38. Then this total diameter is 187.45. 187.45. This diameter is 104.65. 104.65. Right? This height is 4.32. 4.32. Then here this one, from base to this height, it is 43.69. So this one is 43.69. And total height is 98.3. So this one is 98.3. Right? So these are the dimensions. I am creating here only basic geometry. It is a better strategy while creating 3D models. Create only basic shape. So here it is possible to create that groove or center hole also. In revolve command you can create that hole. But hole is a standard feature. So it is better if you create hole with the hole command or hole feature. Okay. So we can create a hole here using the all command, but I have not created that hole in the basic section. So try to keep our first sketch as simple as possible because it will be good for editing. If there is any change in the design, it will be easy to modify. Okay, so as the complications are not here, it will get modified easily. There's other features will not get affected by modification of these features. Okay. So I have kept this as simple as possible. So we will come out of this and revolve it. It is a sharp command and it will revolve. So this is the basic shape of the flange. Now we are creating machining component, right? Now what is next? We will create a groove there, which is at the bottom face. So here there is one groove. So we will create a groove here using groove command. Groove is a material removal command. Okay. So it will remove material in by revolving the section around the axis. Again, I will go for the position sketch and sketch on YZ plane. So here we will create a profile, right? So this profile having this shape. So I can project this edge using project command. Now trim it. These dimensions are given here 6.1, 6.72, this height is 6.72. Then this angle is 66.9. Now these both angles will be same. So here we can apply one more time, or we can make it symmetric, but we don't have axis right now. So I will apply angle again. Now we have to position this. Now its outer edge is at the diameter of 77.77. Right? So this diameter OD from this axis, here I will create an axis again and apply the diameter from this axis. Right? And this one is 77.77. 77.77. Right? So we have positioned it, and now use groove command. So I will remove the material. Okay. Now what is remaining? This hole at the center, right? So I will create a hole there using simple hole command. Hole, position it here on this face. Okay, for positioning we can use constraints like concentricity. So center of this and center of this shaft will be same, right? Now this whole diameter is 54.38. Diameter is 54.38, right? And hole depth given is 65.53. 65.53. Okay. But this hole is counter drill type. Okay. And here the bottom is V bottom and this angle is 90 degree. V angle, right? Now here for this counter drill, the diameter is 64.77. 64.77. Okay, and depth is given 6.35. And again angle is same 90 degree. So this type of hole is there. So we have specified all the dimensions. Okay, basic hole diameter, hole depth. Then the bottom shape is of angular or V bottom shape. Then the hole type is counter drill where there is a counter and counter sunk also. Okay, both are there. Or you can say sometimes it is called as chamfered counterbore. Or after this shape you can see here. So here it is a counterbore and this is the chamfer again. Or you can say counter sunk. And this is the basic hole. And its bottom is also V type. But this hole is not blind hole. It is a through hole, so it should open below. So there is one more hole. We can create it from this side. Okay. So we'll create one more hole here on this face. Locate it. Again, I will make it concentric. Concentric means axis will be same. And here this hole diameter is 46.35. 46.35. Here the hole is through hole, not a blind hole. So I will say up to last. So it will open it in the previous hole. See here it is opening probe. And what are the other dimensions? Okay, nothing. Simple hole. Here we have said on counter drill, but here we want a simple hole, right? So you can just see this. It's a flange. Yesterday we have discussed it's a flange used for power transmitting. As a power transmitting, it's used in a coupling. Okay. So one more similar flange will be there on the opposite side, and this will be on the one shaft, and then using some bush and bolts are on the PCD. Okay, power from one shaft to other shaft is transferred. So what is remaining? There are how many holes? I will just see that drawing. Mm, yes, 8 holes are there. Okay, of 22.35 mm diameter, and on the PCD of 146. So I will create a hole here on this face. again this hole is through hole, and we know the diameter 22.35. First we will position it. Okay, so here it is showing. So I will just locate it here. Now for constraining, you can align this with the center plane, and radially here we can create a circle which is having coincided with the hole, say concentricity. Okay, and diameter, this is PCD actually, and PCD is 146, right? So you can see this color. Green color indicates it's constrained. Now we have to locate this hole. We have said define the center. So it is aligned to the vertical plane. So its x-axis is x coordinate is 0, 0, but still it is our radius is changing. So I will just constrain it on this circle, coincide, right? So here there is a hole of 22.35 mm diameter. So we want a through hole. So here we will say up to last and say preview. Okay. Now we have a hole here, but we want 8 holes, equi-spaced. Okay. So it is equally spaced. Now we will pattern it. Pattern, circular pattern. Then I will select the object first. Object is this hole. You can select it from the tree. Okay. So this hole I want to pattern. Reference is this hole, center hole, means axis should be there, means as a reference we can select axis, and axis for this pattern and for this hole is same. So I will select this hole. You can select any circular face or cylindrical face. But I want here there are 2 holes only, so I want 8 holes. But 8 holes I want on complete PCD, full circle, right? So in case when we need full circle, okay, around total 360 degree. So here there is option complete crown. So you can use complete crown option and define number of circles, right? So here we have created 8 circles on the PCD, correct? Now all the basic features we have created, right? Means material addition and material removal, correct? So we have created holes. Generally, at the time of modeling, it is better if we create all these basic features first and then go for dress up features. Dress up features means fillets, chamfers, and all. So once we have finished with this basic features, we will first save this model, and now I will add fillet and chamfers here. So first we'll go for fillets. So this fillet here at this edge, it's 9.65. Okay, 9.65. Now one more fillet. Just we will check where are the fillets. Here this fillet is 3. It's 3 mm, right? Then one more fillet is there of 1 mm radius. So here for this edge there is a 1 mm radius fillet, right? Anything remaining regarding fillets? No. So we have applied all the fillets. Now we'll go for chamfers. Okay. So here this is a hole, and generally at the entry of hole there are chamfers. Okay. So for the easy entry of the shaft inside the hole. So this chamfer is of 1.25 52 into 45 degree, and I will select just this edge. So this is the chamfer having 45-degree angle, so no need to specify or change the direction of chamfer. Now both these chamfers, this one and this one, both are again 2.28 into 45 degree. So here also there is a chamfer. Yes, so one more chamfer is here at the top. So I will apply chamfer here. So this is also 6 into 45 degree, right? And one more chamfer at this edge, very small chamfer here of 1 mm. Mm, okay, so this is our finished product machining component, right? It's a ready component, ready to use. Now we have to manufacture this as a with a forging process, right? So what customer will do? They will send IGS files of this. Okay, so you can just see this part. Okay, but while designing a forging component, this will be ready with you. Means this is given by customer. This is the finished product. Now out of this we have to create a die, right? So first I will save this as a IGS file. So I will go to file and save as, say, IGS. You can create a state file also. These are the neutral file formats, means when you want to open this model in new software, then we can use IGS state or any other formats. There are different formats, neutral file formats. But here just we what we want is we are going to open this in same software, say in Katia only. But here important thing is we want a dump model, means with the without features. Means here you can see all the features are there. Everything is listed here. This is called a specification tree, and in tree all the features are available. Means at any stage we can modify any feature here. There are different fillets, chamfers, holes, pattern. First we have created a shaft, then groove, then the holes. So everything is available in the tree, right? So we can modify these features anytime. But in case of dump models, if this tree is not available, so I'm going to save this as an IGS file, and we will open that IGS in Katia again, right? So I'll go to file, save as, and say here IGS, right? Same name, flange machining. So we'll close this file and open the IGS file. I'll go to file, open. In the same folder, we can have IGS file, flange machining. Where is flange IGS? Yes, flange machining IGS. So this file we will open here, right? Oh, this is surfaces. So here one problem is it is open. It has opened it in surfaces, in surface form. Okay, so you can see this. I will just hide this. It is in the form of surfaces. But I'm not sure whether it is correct or not. Correct means there might be chance that some data may get lost and some gaps are there, some surface is not opening properly. So we will again create a IGS with solid output. Okay. So I will just close this, open our basic part again, our from Katia I will open, and I will do some settings here, tools and options. Here it is IGS. See here, there is a setting for exporting. Export any file as a surface. Means if you want to save this file as a IGS file, so while exporting, this will say export it in IGS surface format. But what we want? Solid, right? So we want solid now. So I will just save this option as a solid. Again, we will save as this file as a IGS. So we will overwrite that file. Now open IGS again. Open. Just a minute. So we'll open that IGS file. Now we can see this is solid model. Okay. So what it changed means we have created the file, and here we have opened this IGS file. It's not a cat part file. Means it is not a CATIA file. Okay. So what it changed, you can see here. It's a part body only. We don't have any feature here. We have used sharp, we have used glue command, we have used fold command, we have used fillets, chamfers, number of features we have used. But now this is a dump model, only volume. Okay, so there is no history of this component, right? Now this is what we get from the customer while creating a forging component, or we want to build it, right? So I will just rename this as a forging flange forging cat part. IGS file I have saved with cat part file. Now this is a CATIA file, right? So again, if we want to make IGS out of this, means for machining purpose, we can create a IGS also. But if we use some features on this dump model, then it will be recorded here in the specification file, right? So what we will do, we will delete unwanted uh, features, means we will delete those features which cannot be created using forging process. So in tracer features, there is a command called delete faces or remove faces, right? So I will just go to the remove faces option, right? Before that, I will just make it define in work object. So we are working in part body. So I will change the workbench. So here I want to remove these spaces, right? So these holes are now removed. Okay. So again, this hole is also I want to remove. So we cannot manufacture this using forging process. So we need to select all the faces. Okay. So we'll remove this face also, right? Now there is no hole. We don't want these fillets also. Right now we don't want, but we will apply these fillets as per our forging requirement. Now we don't want this dimension currently. So I will delete this face also, this fillet also, because here at this age we want fillet, but with different dimension and but at different level. Okay. So I will delete this face also. All fillets, chamfers, everything I am deleting. Okay. So this is the basic shape only. Now, I think you might be thinking that we are coming again to basic shape, very simple shape. So instead of taking IGS and instead of doing all these things, we can create this basic shape again. Yes, that is also possible. So instead of taking IGS from the original component and deleting all these features, okay, and just go on designing new feature forging component. It's okay for simple components. This is very simple component flange, so it's very convenient to create a new part, totally new from the scratch. You can create this part easily as a forging component, but consider very complicated parts, parts like crankshafts, having very complicated shapes. So creating 3D model of crankshaft is very critical task. So creating it again is definitely difficult, or we don't know all the designing concepts done by. Okay, means we are getting it from the customer. Means we don't know their design procedures. So it's better to get 3D model supplied by customer. Okay, so this is supplied by customer. So we are not going to create a 3D model here while for designing forging component. Okay. So again, we will delete this also. It's not required. Actually, this is a machined feature. So we will delete this also. Mm, So one thing we can do here is you can fill the surface using some revolve command, or I will try it by thickness command also. Let us try thickness command. Yes, but we should have proper value of thickness. This depth is 6.72. In the machining, we have specified that 6.72. So you can feel it like this. So using thickness command, I have filled it, but you can use different command to fill that area. Okay. By any way, you can fill that gap. Now we have basic shape. Now what we'll do? What is first step? We have to fix the parting line, location of parting line. Do you remember what is the guideline while defining parting line? Okay. So parting line is always placed in a maximum material area. Okay. So this is the maximum material area. This one. Alright. So we will define a parting line here. Meanwhile, I will just make visible. These planes are now visible. Okay. So we want parting line somewhere here. Okay. So this total height is I think 46 or something like. I will just check. So this from bottom it is 43. Okay, so right. So at 43 means 21.5, right? 21.5. So we can make it round figure like 20 also. So from the bottom, I will define this plane as at a 20 mm. Okay, at a 20 mm distance, I will just create a plane, and this plane can be used as a parting line or parting plane, you can say. So from the upper part, above this plane, this newly created plane, above this plane, that part will go inside the upper line, and this part will go inside lower line. Okay, just see this parting line. Now what is next thing? We want to add some machining allowance on this, right? So how to add machining allowance? So we will add machining allowance of 3 mm, right, everywhere. So we can use thickness command, right? So thickness of this. So here there will be problem. We will see. I will just remove that case because we may face problem here. This and this, and for this surface, we will add thickness of 3 mm, right? See, so everything is increased by 3 mm. This diameter also we will increase by, okay, 3 mm. Actually, thickness we are increasing 3 mm, so diameter will be increased by 6 mm. Okay, here also 3 mm, right? Now here we might face some problem. I will try it again. For this surface, okay, yes, we have, right. So here also we have increased the thickness 3 mm. Okay, so we'll check here how much space is available. This is the inspection tool, and we can check the space available between these two surfaces. It's 4.33. Yes, sufficient. So this is our component after adding some machining allowance. You know machining allowance because for forging we need some extra material, right? After forging we need to do machining. Secondary machining is always required because for the fitment we need some good surface finish. So generally for fitment features we are applying machining allowance. But here in this component all the faces are having machining process after forging. So here we have added machining allowance everywhere on all faces, right? So already we have defined here parting plane, right? Now what is next? We have defined parting plane. So guideline for the parting plane is it should be in a maximum material area, right? Or the thickness means it should be the level of parting plane should be somewhat less than the half of thickness. So this is around 45, 46. So we have placed this plane at 20 mm from the bottom. Okay. So we have considered this at 20 mm from the bottom, from here. This is our parting plane. Now we need to apply draft. Okay. So you can just imagine for which faces we need a draft. Hmm. So for drafting, for draft angle, The draft angle is applied perpendicular to the parting line, parting plane, right? The face which is perpendicular to the parting plane. Okay. So for these faces, this is the cylindrical face. So here we need a draft. For this face also we need a draft, and for this small face also we need a draft. Okay. So on these faces we will apply drafts. So here we will apply a draft of 5 degree. Okay, as this is a steel, made up of mild steel or steel, you can say. We don't know exact composition of material. But here on this face, depending on size of the component, we will apply 5 degree draft. And on this face, it is 3 degree. Okay, so here it is 3 degree. But you can just think of this is the parting line. So in the upper part, above the parting line, the draft should be like this. Okay, and in the lower part or below parting line, draft should be like this. So here at the parting location, material will be maximum, right? So here the draft direction is like this, tapering to the bottom side, and above the parting line, the taper direction should be Z direction or upper direction. So taper will be in this direction, and below the parting line, taper will be in this direction, because here this is the pulling direction, and here this one will be the pulling direction. In this direction, the die will be removed, or here in this direction, in downward direction, the die will be removed, right? So we need to apply drafts here. Okay, we'll apply here. It's a very simple draft, 5 degree draft. Now this diameter is known, or we want to maintain this diameter as it is, right? So if you know draft command, this is a draft for taper. We need to define faces to draft. This one is the face to draft. Now it's asking for neutral element. So if you know neutral element, what is neutral element in CATIA is better. Or if you don't know, neutral element is the section where this size is kept constant, right? So if we can select this as a neutral element, or we can select this as a neutral element. Generally it is perpendicular to the faces to draft. So if I select this as a neutral element, sorry, if I selected faces to draft, this is the faces to draft, and here I have to click and then we select neutral element here. Okay. So if I select this as a neutral element, what will happen? It will remove material in this direction, right? Taper will be in this direction. See, you can see the pulling direction here. So taper will be in this direction. But if you keep this taper in this direction, here it will remove the material. So there is a chance that this part will be undersized. After machining, we have added machining allowance here. So that material, extra material which we have already added, that will get removed. So there is a chance that this part will be undersized. Okay. So we don't want to remove this material here. From the top section, we don't want to remove material. Okay. So it's better if you define this as a neutral element. Okay. So I will define this as a neutral element, top face as a neutral element. So here I will select this as a neutral element. So here it will keep the material same as it is. Cross section will be kept constant. Okay. So here it will not remove material. But in this case, taper will be in this direction, so it has to add material in this direction, in the opposite direction, or in the opposite to the pulling direction. So taper will be like this, so there will be material addition. Okay, so 5 degree, so there will be material addition, right? So there is a draft angle. We have drafted this piece. We have applied a draft angle to this piece, right? This area we have kept constant. This cross section we have kept constant. Now here, this is very small face. So for this face also we will apply fillet, draft angle, draft to this face. Again, It is advised to keep this as a neutral element because here we want to maintain the cross section. Okay. Material addition will not create a problem. Material removal may create a problem. That in that case, part can be undersize. Okay. So here for small face, I will just apply 3-degree draft. Right. Now this pulling direction should be this one. Okay. Because here it is a lower part. It will go in lower die. So it will be like this. I will just check. Yes. This edge is came out right now. Means pulling direction is correct. Taper should be in this direction. Okay. Now critical part of this component is applying draft at this location. Okay. So here we need to maintain these diameters constant. We don't want to change this diameter because again the same problem may appear that this part will be undersized if we remove material from this sides. So we cannot apply simple drafts here. Okay, we have to go for some advanced feature. So advanced draft is there, advanced press of features. So here it is advanced draft. So I will go for this one, draft both sides, right? So for this component, we don't have fillets here. So no need to use these fillets. Here we can see this preview. This is called as a reflect line fillet, but we don't want to use this reflect option. So instead of that, I will go for neutral option because we want to apply fillets in both the directions. It is called as draft both sides. Means uh, this plane will be the parting plane. So we will have draft in opposite directions. Two drafts on this face in opposite directions. Okay. Above this plane, the taper is facing towards upward direction. Below this parting line, below this plane, the draft is facing downward direction. Similarly, you can see in this preview. This is parting line. This here they have used surface as a parting line. So below surface you can see draft is like this, and above this surface you can see draft is like this, right? So this is the parting line, parting plane. Okay. So we want similar draft. But here our parting plane is flat, simple plane, not a surface. This is the parting element here in this case. So in components like crankshafts, they are using such complex parting elements to have different shapes. Okay. Crankshaft is very complicated shape to create a model, to create a die. Okay. So here we have to select parting element first. So this is our parting element we have already defined. Then the neutral element. Now here we are applying draft on both the sides, right? So there are two different neutral elements. Okay. So here we have angle is 3 degree. First neutral element will be this one, and second neutral element will be this one, right? So between these two faces, we want to apply a draft, and we know angle from this side, and that angle is 3 degree, which is given to you, or we can apply as per our guidelines for the forging purpose. What should be the draft? We know the guidelines. Okay, as per the material draft angles guide. Okay, so this is the neutral element 1, this is the neutral element 2, and we have to select here faces to draft. Now you can see this option, computation method is fitted. So what do you mean by fitted type of computation method? So here it will create first draft of 3 degree up to this parting element, and the face will come out of this diameter. So it will create a taper here, and this downside draft will be fitted with respect to upper draft. So with respect to this draft, the bottom draft will be automatically adjusted, right? So software will do these calculations itself. No need to do some calculation because this distance is not equal. See, we have created parting line at some lower level. This is not exactly divided in half parts. Means this is not exactly at half. This plane is at somewhat lower level. So definitely these angles will not be same, right? So as per trigonometry, we can calculate these distances, but again it is hectic or laborious. We need to do calculations. But here there is an option fitted. So lower draft will be adjusted automatically using this option. So you can just say OK, say this draft. Okay. So here material is not removed from these faces, these edges. So this is kept constant. Here also it is kept constant, and material is added in this direction. Here at this location, material is added. So additional material we can remove while machining, but we don't want undersized component because we have to do machining also. So after removing material, part should not be undersized. We want to maintain the diameter. So this is important task. We have finished it. Means we have applied a draft here. Now what is remaining? We have to apply fillets as per the guidelines of forging design. Okay. So here I will apply fillet. Okay. Fillet of 8 mm. Right. Here we will apply fillet of 5 mm. Fillet area can be changed. Whatever I have provided in the presentation for just a guideline. So here we will have it 6 mm. Okay. So this is our forging component. Here also we need a fillet. But here I will tell you one important feature of CATIA. Actually, in a forging drawing, I have shown you the forging drawing. We have the space. I have checked it last time. I think you might remember. This gap is 4.32 mm. Right? So once again we will check it. 4.32. Okay. But here the fillet given is 5 mm. So if I go for 5 mm fillet here at this corner, it's not possible because that much space is not available here. Okay, if you know, fillet is a quarter circle, right? When we apply fillet here, the calculation behind that its section is a quarter circle. So we cannot fit a 5 mm radius fillet with a space of 4.32 or less than 5 mm gap. So here we need to use some different features of CATIA. One solution is there is fillet at this edge also. Okay. So first apply this fillet of 1 mm. It is given as 1 mm, and then go for this fillet. So it's basic or very simple solution. Then it is possible because in this case we have extra space available. Okay, so here by after applying fillet at this edge, we have extra space and we can apply fillet of 5 mm easily. One more solution is, I will just undo this. In fillet, again I will apply fillet here on this edge, fillet of 5 mm. And if you click more options, there is an option edges to keep. So I will select this as the edges to keep. Okay. So here it is very easy to adjust the fillet. Means it will adjust the space on this side. Okay. There are different options for circle creation. If you revise your geometry knowledge, we can create a circle of center and radius form, or we can create a circle using 2 points and radius option also. So here it has software has used 2 point and radius method, right? So this is the first point. Here tangency option is there and radius is also given. So it will change the different method of yes sir. Hello, is there any problem?
No,
Some,
sir.
hello.
Yes, sir.
Someone has raised the hand.
No, sir.
So
No. What we have done is we have added students so that they can give the feedback after the end of our session.
Okay, okay, okay. Because someone has raised the hand, that's why I thought there is some
No, no,
problem.
sir. No, no issue.
Okay. So should I continue?
Yes, sir.
Okay. So again, we will apply fillet here, fillet of 1 mm, right? Okay. Now maximum means mostly our forging part is ready. I think I have shown you the image in presentation. It is similar to that. This is our forging part. There is one more hole here, a simple hole for guiding purpose, means to fit this component in a die cavity. So we'll create a hole there of 35.63 mm diameter. Okay, a simple hole. We can create it by glue command or by simple hole command, or we can use pocket command also. Okay, so again, I will use your pocket command. It will be easy to understand. So here I am applying, creating a circle of diameter 35.63, or you can create a hole of 35 diameter. Means because after that we are going to create some larger hole. So 35 is also okay. This diameter also is okay. Again, we will cut it up to the depth 12 mm. Okay, so we will use a pocket command there for the 12 mm. Now see, we have created this pocket or a cavity for holding purpose, means after all at the time of machining there is a hole. So for positioning purpose, for positioning this component inside the die cavity, it will be better here to have some cavity. Okay, but as we have added a cavity here, there should be fillet again for easy material flow. There should be fillet, and there should be some draft angle also, right? So I will apply fillet here. First we will apply draft angle. It's better. Then we will apply fillet. So draft angle, it will be simple draft of 5 degree, or this space is very small that, so we can use some extra angle here, 10 degree. And this is the faces to draft. Pulling direction should be downwards, because here in this direction we are removing the die, right? So see, it is adding material inside the cavity. So we should, means it should add the material. If it removes the material, see, if I reverse this direction, pulling direction, see what will happen. So it is removing the material. So the cone, see the cone shape. Okay, so it is removing the material. So if I apply a draft like this, see here, we cannot remove this component from the die cavity. It will get stuck inside that die cavity. So this cavity or this should not be there like this. Okay, you have to reverse the direction. This is the wrong direction. So this is the pulling direction. See the draft. It is adding the material. So now we can easily remove this component from the die cavity. Correct? Now we will apply a small fillet here. Okay. Right. So this is a cavity at the bottom. Now we have our forging component. So from the machine or finished product, we have designed a forging component, right? This one is a forging component. We will save it first. Okay, plant forging. Now what is remaining? We have to create a die. Means two die cavities will be there, upper die and lower die. So we have to create dies first. Using this forging component, we can create a die. For that, we will create a new component. Okay, new part document. We'll go for new part. So here I will say upper die. So this is our new part, right? And now we know. parting line defines two dies, means two dies get separated from the parting line, right? Okay. So while creating a die, we have to start from parting line, and we know that parting line we have defined above this plane at 20 mm. If you check the part, this is our basic coordinate system, basic plane, XY plane, and above that we have created it at 20 mm distance. We can check that distance also. It's at 20 mm. And when we copy this part for die creation, it will get placed in similar way, means this part will get aligned like this only, means z axis will be parallel to z axis, x axis will be parallel to x axis, similarly y axis. So everything will be same. This will be positioned on this plane only, on the basic, means this will be the support, xy plane will be the support. But we want dies here should start from this parting plane. Below this parting plane, there is lower die. Above this parting plane, there is upper die, right? So I will go for die creation and first create a plane again at 20 mm, and I will create a sketch on this plane because from here we have to create a die. So our basic diameter of the component is around 200 mm. So we need some extra spaces there. So I will create a larger circle of diameter, suppose say 200 or 300 mm. Okay. So there are not many features in a die. There are land, gutters to handle that flash coming out of the forging process. So this is having some larger diameter. So I will just pad in, this pad feature. Height you can adjust as per the component height. So basically this is upper line. Okay, very simple shape, circular face. But here we have to create a cavity similar to the forging component. So just for understanding, I will change the color of this part. Okay, so this is our die. Now what we have to do is we want cavity here inside this die for the forging purpose. So I will go to the forging component. This is our forging component, right? Again, for this component also I will change the color. Or there also after pasting this component there, we can change the color. So I will just copy this body. Okay. So just right click on the body. Don't right click on this part document. Okay. Right click on this, say copy. Go to the die part and paste it here at the part document. Don't paste it in the part body. Generally, people are doing this type of errors. That's why I'm uh, clarifying it in advance. So just paste it here. But while pasting, don't paste it with the normal procedure. Go for paste spatial. There are two options: paste and paste spatial. I think you might be aware with some Excel or Excel sheet also Excel. There is option paste and paste spatial. So in paste spatial, we will get some different options like as specified in part document, means here it will come with all the features, means all the listed features, planes and whatever features we have used. But we don't want that. We want as a result with link. Means we want only result of the forging component or the ultimate result, whatever the final volume we have created in the forging component, that volume we want. But with the link, means in future, suppose if we modify this component, see here it is solid only. If you go to parting forging part, see we have used different features. We call that product body from IGS file, then remove some features, then applied some thicknesses, applied draft angles, fillets, lot of things we did here. But we don't want all these details. Here we want only volume. So this volume is pasted here. We have this volume. But again, important thing is this is linked with the original component. You can see this green dot here. This green dot indicates this component is linked with the original component. This is having link means if you modify this part in a original component, original forging component, that will get reflected here directly. Directly this will get modified. Okay, so there is a link between this component and original forging component, and that's what we want. Okay, now we want here cavity. We have pasted the body. This is a solid body. It's a positive body, but we want here negative side, means negative volume. We don't want material here. We want a cavity. It's a die, right? So we will use Boolean operations. You might be aware with Boolean operations: addition, removal, intersection. It is available in mathematics also, right? Yes, these are the Boolean operations. Okay, so here you can find this remove option, add, remove, and intersection. So we use remove option. Remove. What we want to remove? This body. From what? Part body. And say OK. Now there is a cavity. Right? So this is our upper die. We can mount it on a press machine or hammers. Okay? And use for forging. Now there are a lot of features. Again, land or gutters still to create. But this is just a cavity creation. Means we can just create a basic shape of the die. And this is upper die actually. We can save this file. But what is different for lower die? Here also we can have lower die in the same file. What we have to do is just change its direction. Change direction of pad. If you pad it in downward direction, see, here it is a lower die. Okay. Now here you can see this sharp edge. I have kept it sharp intentionally because we don't want sharp edges everywhere. Everywhere there should be some smooth edges for the proper flow of material inside the die cavity. So what I will do, I will just modify the component in the original file, and we will just check whether this edge will be smooth automatically or not. We'll go to forging component, and here there is no fillet. At this edge there is no fillet. That's why there is a sharp edge. So this is a original component, and here we will apply fillet. Fillet of suppose 5 mm. Okay. Keep redo. Now we'll go to the die. See, this is red now. Means it is asking for update. Okay. So there is some modification, and it is asking to update us. So if I click on update, this will be modified or updated automatically. See here. There is a fillet added. Okay, like this you can change anything. You can change diameter of the flange, you can change draft angles, you can change size of the component, anything can be changed. Same will get updated here automatically. No need to modify again. This is the advantage of these tools, CAD tools. This is possible in CATIA, this is possible in 3D graphics, this is possible in Creo, this is possible in any other 3D modeling software. Means I'm not saying this is a feature of CATIA only, but these types of advanced things are there in CAD tools, means CATIA or any 3D modeling software. So this is called as Boolean operation and designing actual component. Means generally what is happening or what misunderstanding we are coming through the students is they just learn pad, pocket, shaft, groove, hole, pattern commands, and they are saying now, okay, we know CATIA, I know CATIA, I want to go for this advanced software, something advanced I want. But lot of features are there in CAD modeling softwares. It's not only modeling, you have to link your basic engineering with this CAD softwares. Then it is quite useful. Means it's not like that keep learning pad and pocket is CATIA, okay, done CATIA, I know CATIA, I can work on CATIA software. But lot of things are there, power copy, design table, surfacing. Surfacing is quite interesting part of CATIA. So lot of things are there. While learning, just be sure that from whom you are getting this knowledge and all. So this is all from my side. And for if you want these two separate files, you can save as, you just reverse the direction and save as the file. Okay. So here it is upper die, but if you want lower die, just reverse the direction. Here we have created lower die. Again, I will change direction. Okay. So this is upper die. Okay. You can save this file using save as command, save as lower die, and just reverse the direction. You will get lower die. Right. So this is from my side. If you have any doubts, you can ask. You can post on YouTube. You can ask directly. Yes, sir.
So anyone having doubts?
Regarding forging process or regarding the yesterday's concept of second moment of area.
No queries, sir.
Regarding forging process or regarding the yesterday's concept of second moment of area. Process or regarding the yesterday's concept of second moment of area.
So there is no queries, sir.
Okay, no problem. Yes, sir. So what is next schedule?
Morning, sir.
Yes, sir, you can speak. Or good day, sir.
Hello.
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 Yes, sir.
Hello, good day, sir.
Good afternoon.
Good afternoon. Now I'm having some concluding remarks on the 2 weeks internship program, student internship program for the BTech, S5, T1, and final year BTech students.
Okay.
Uh, at the first, I am very much thankful for your team and yourselves that you have shown us a keen interest to organize fully on your own and CAD/CAM Guru such types of internship, student internship programs, which was started from the 13th of July, isn't it? Hello.
Yes, sir.
Now, the program is very interesting, very useful. The topic of internship was the mechanical to be a, I mean, a prerequisites to be a mechanical design engineer in which most of the students, not most, many of the students are have lost the knowledge of the drawing and dimensioning the drawings. That is what we have taken a total care during this 2 weeks internship program.
Yes, sir.
However, the first week was uh, only devoted towards the geometric dimensioning and tolerances. No doubt, we are teaching these subjects in the classroom theory, but actual
Right.
practice is very less, and the students are not understanding the how to give the dimensions and tolerance to the product.
Right.
We expect always the students should draw the working drawings which can be directly used at the production floor level. So in this case, for the 2 weeks, you are concentrating on the such types of the knowledge which is basically required, and the basic things are incorporated in the these 2 weeks. However, we have the incorporated the CAD tools which are used in modern practices. And along with this, CATIA is added for 2 days, in which you are shown how the CATIA is useful in the drawing purposes. And these 2 weeks will be very much useful for those who are having the interest in the design, research, and production, where they can read, write the drawings also, and they will be able to produce the working drawings or production drawings when they are subjected to the industrial work. Our students will also gain the knowledge of these, the geometric dimensions and tolerances, along with a drafting tool, how to use the drafting tool in modern practices, and how to use the CATIA also. Your keen interest and keen knowledge in the this topic is appreciated by our students and the faculty also.
Thank you, sir.
So at the outset, I am once again very much thankful for the CADCAM group and your team and Shirarkar sir and remaining part, remaining faculty from your CADCAM group also. We have been in touch with you from 2007, and the interrelationship between our institute and the department with you and your institution results into this fruitful success of student internship programs. Once again, I am very much thankful for your advice, guidance, and teaching learning schemes which you have provided for last 2 weeks to our students and the faculty also. With this, I conclude the total 2 weeks programs which are used for our students and faculty how to inculcate the teaching learning process in the coming era. Thank you. Thank you very much.
Yes, sir. Thank you. Thank you, all of you.
Thank you.
I request Hargesh sir to give vote of thanks, please.
Sushant sir, good
Sir.
afternoon.
Good afternoon, sir.
Yeah, I'm meeting you first time.
Yes, sir. I will
Hargesh sir,
definitely come to college whenever I visit Kaulapur. I am from Kaulapur only,
okay,
and
okay,
whenever I will be there, I think I'm planning for next week, and definitely
okay,
I
sir.
will visit in college.
So we welcome you to our institute whenever you come to Kolhapur. Okay. On good afternoon to all. On behalf of Mechanical Engineering Department, our principal sir, Dr. D.V. Gevde, and the management of PVPIT, I am very much thankful to Shirakar sir and especially Sushant Mole sir, directors of CADCAM Guru, Pune, for conducting this 2-week internship program on prerequisites to be a mechanical design engineer for our students. In present COVID situations, for our student, it was very difficult to complete this internship program, and in our D-Part curriculum, internship is compulsory. So you provided for our students this facility by taking the efforts. So I'm very much thankful to CAD/CAM Guru and both of you, sir, and your team for sparing your valuable time and sharing most important and that is useful knowledge to our students. I'm also thankful to Professor N.V. Argude, sir, Dean R&D, who is in constant touch with you and due to which we are able to organize this internship program. I also thankful to our team members, especially Savan Wani sir, Sheetal Gunjate sir. They have taken efforts from last 15 days to manage this program, organize this program. I am also thankful to our principal Dr. Gevde sir, Honorable Trustee Amit Dada Patil, Honorable Chairman Sahib Vishal Dada Patil for their constant support and encouragement for organization of such type of programs. Sir, in these 2 weeks, you have shared lots of knowledge regarding the CAD/CAM tools and the geometric dimensioning tolerances, etc. Now, I'm sure that our student will practice that tools, whatever you are taught. And I'm sure that some of our students will become a best design engineer in future. And I'm lastly, not but least, I'm thankful to all the participants. Sir, do you know nearly 1 participants have participated in this internship program? I also thankful to all the participants who have attended this program. Once again, I thank you, all of you. Thank you.